see those? Okay, we're going to take a look at one end of them now. And if you got your glasses on, you can gather a good bit of information from this. You notice the point of origin there is Finland. So that gives you some idea where those capacitors came from. They're self-healing, if you notice, and they're also have some other characteristics. It's got the kVA written on there, if you can read it. But the combined kVA of those two capacitors is about 30,000. And the fact that the device that your input is about 12 volts at maybe 30 milliamps or something like that. And that goes into the inverter, and the inverter is tuned back so that only a tiny bit of that is going forward. So whenever you come to the output, you basically sent forward maybe 2 or 3 volts, and you're getting back, say, 30,000 kVA. So the computer program that I like to use with this type of situation, it won't work with this one, but it will work with that one down there, and we'll talk about it a little bit. But I sit down and for days run computer programs on these things before I even start building them, and then I correct as I go along. I start taking readings as I go along, and then I start building corrections into the device. And we'll see that in some detail in a little bit. Okay, we're going to the one that's on the floor down in front of us. And let's see what happened here. There we go. See that okay? Okay, the parts of this particular device here, up to this point right here, is what you're already familiar with. Now, there's 2 or 3 things that are built into this which are new and different from what you might be thinking about. Here's the inverter again, a smaller sized one. Here's the variable device on the end. It's coming into a neon tube transformer, which is here. That neon tube transformer has 2 high voltage outputs. Those 2 things are brought over to here and underneath here, and they're joined together by a couple of diodes. So the high voltage output is going through this one right here and coming in at the base of the coil that's inside the spring there. And it's coming out at the top end and coming back this way and going to here. There's a lightning volt protector here that's serving as the case of the spark gap. So there's not a spark gap as anything that you would recognize. Okay? Once you get over to this point here, 2 things have happened. One, I calculated the L1 coil, which is on this sliding 2-inch PVC tube inside the 3-inch coil. It was calculated to be 1/4 the length of the wire that's involved in this L2 coil, or the outer coil. And the reason for that is that coils have both capacitance, inductance, and resistance. And all those things play part in the tuning of the thing. But since you started out with about 1/4 length of the longer coil, you're pretty much tuned. You're almost tuned immediately. And as it turned out, of course, you have to put a capacitor on one of the 2 coils. The easier one to work with is the L1 coil over here. And you can put a capacitor in there that will correct for any slight difference that might be. And those things are usually into the like 1/10 of a microfarad or something along that line. And as it turned out, when I put that thing in and then I took a reading on the circuit, well, it turned out that I had a 0.5 6,000 volt capacitor that I could put over here, and I had an exact tune on this thing, even though sliding this coil in and out is meant as a tuning device. I could have tuned it by doing that. But as it turned out, the thing was exactly tuned without even moving the thing by using the particular combination of capacitors that I used. Okay, with that in mind, the next thing is that in order to have useful energy, you can't go directly from this coil system and use it. You have to have some way of storing it, and the storing options are basically either battery or capacitors. And as it turns out, capacitors are, we'll come back to that later, capacitors are probably the best option because they can be built to where they're self-healing, they can be built to where they have over 40 years of useful life that's known. They've tested some of them and they know that they will last 40 years without any sort of damage if used in the proper manner. So a battery has a useful life of about 1,000 cycles. So if you're going to use a battery system, you're going to be changing your batteries pretty often if you're going to be using a lot of electricity because you're going to be cycling them quite often. The capacitor, however, does not wear out. It cycles at millions and millions of cycles a second, and it goes well beyond 40 years. So that's the correct option, and I'll show you a chart later on from one of the battery manufacturers that backs me up on that. Okay, we're going to another photograph here, and that's okay. We're walking around this one. We're going to walk sort of a circle around it and see what's there. We were talking about the variable neon variable deal for letting the amount, making the tubes brighter or dimmer. It's made different than the dimmer switch that's in your house. So you can switch the tube, but you probably come to grief if you use the house dimmer. These things are maybe $30 a piece, depending on where you're at. Of course, here's the neon tube transformer, and it's built with an earth ground coming out on the other end there, so it's center tapped, which means it has capability of making amperage for you. Without that center tap, you wouldn't have the amperage available to you. As a matter of fact, as you lower the voltage in, the amperage goes up on this thing. So if you run it at less than 110 volts on this inverter here, and then you back it off again with the variable deal, you're going to end up with, in some cases, more amperage than the device can handle. So you can melt it. Okay.